Hello, everybody. I am Angelo Auricchio, Editor-in-Chief of Arrhythmia Academy, and it is my distinguished honor and privilege to welcome an extraordinary guest, Professor John Rogers. Welcome, John.
Hi.
Professor Rogers has a very impressive curriculum vitae. He is professor at Northwestern University of Materials Science and Engineering at Biomedical Engineering and Medicine. She's also have affiliated appointments in medical engineering, electrical and computer engineering and chemistry, where he is also director of the Query Simpson Institute of Bioelectronics. So someone who is very extraordinary and a little bit outside the field of medicine, but I can tell you he is really very in-depth in what, and probably is really a start for what we electrophysiologists, we cardiologists are going to do in the near future. He published more than 850 papers, so impressive numbers. I don't know when you had time to do all this great work, and his research has been recognized by many awards. He has recently co-authored one of the most fascinating articles I read during the last couple of years that has appeared in the very prestigious journal Science a very few weeks ago. The article is entitled A Transient Closed-Loop Network of Wireless Body Integrated Device for Autonomous Electrotherapy. Again, a fascinating article. And now, without any further ado, I'd like to ask Professor Rogers to tell us more about the technology, the application, and of course, what is his future vision, where we should go with all of that. Thank you very much for accepting our invitation, and I'm sure our people will be very happy to listen to you and be fascinated by all the ideas and great work that we have done. Thank you so much.
Yeah, great. Thank you for that kind introduction. It's a real pleasure to be here and to have a chance to share some of our research with this particular community. So as you mentioned, we published a paper recently kind of introducing an idea around autonomous temporary electrotherapy, focusing specifically on cardiac pacemaking following a cardiac surgery process where patients are currently managed using temporary but otherwise kind of permanent pacemakers that need to be removed after a period of need. And as engineers, we began to think about maybe a more attractive alternative to that sort of approach that would reduce risk profiles for those classes of patients. And we launched this effort in response to an inbound request for a technology of that sort through our cardiology department here at Northwestern Medical School. So I'll give you a quick kind of 10-minute overview of what the technology is all about, and then I think we'll have a chance to engage in some questions and answers. And if there's anybody out there who would like to follow up by email, feel free to shoot me a note, and I'd be happy to answer any additional questions we aren't able to get to today. So the title of this short presentation is the same as the title of the paper that was published, specifically a transient closed-loop network of wireless body integrated devices for autonomous electrotherapy. Again, focus on cardiac pacing, but with other application areas as well, specifically in accelerated neurodegeneration associated with damaged peripheral nerves, where we have some parallel activities. So I'll begin with a background, a little bit of an overview of the technology foundations, which really include two component parts. One involves a wireless soft electronic platform that mounts on the skin for monitoring and delivering power to an implanted device that is uniquely characterized by its construction using materials that are entirely bioresorbable. And that's the component of the system that's actually providing the electrical stimulus to pace the heart. So as was mentioned, I'm an engineer. I'm not a medical doctor, but we have deep collaborations across the medical school here and the broader medical complex in Chicago. And so we work very collaboratively in very intimate, team-oriented efforts, to address unmet patient needs with new technology platforms. So that's kind of the idea. We're part of an institute here, and I just wanted to mention that is uniquely kind of set up to facilitate this kind of work at the boundaries between engineering science and medical science. And so it allows us to really take new ideas out of a kind of academic engineering lab scenario and setting, and really move it into prototypes that can be evaluated ultimately on human subjects. And so it's very much translational in its orientation. And I think it's a fairly unique mechanism for driving progress in this sort of direction. And so that institute is providing the funding for the work that I'll share with you today. So as I mentioned, these systems consist of two kind of subsystems. One involves a sort of soft skin compatible electronics. The other is the implantable component, which, as I mentioned before, is a piece of electronics, but unusual in the sense that we build that electronics out of materials that are entirely water soluble and dissolvable in surrounding biofluids over relevant time periods to address clinical needs. And so let me step you through the basic aspects of those two subsystems that make up this entire approach to treating cardiac patients. So the first challenge, and really a common challenge associated with both of those technologies, is that they're radically different than the kinds of electronics that support the consumer electronics gadgetry industry, which is based on silicon wafers and advanced CMOS circuits, very, very powerful classes of technology, but not very biocompatible. Neither from the standpoint of the geometry or the mechanics. These rigid planar devices don't match well with the kind of soft, curvilinear, time dynamic surfaces that one encounters in the natural world, living systems, human body in particular. And furthermore, they're built out of materials that are in some cases intrinsically incompatible with biology. In other cases, support permanent functions. We're really kind of where the engineering has been oriented around silicon integrated circuits, is to make them last forever. And in many medical contexts, you don't want devices to last forever. I guess a resorbable suture would be a classic example of that, where you need the construct or the device for relevant time period, but ultimately you would like it to disappear after it's no longer needed, to eliminate what would otherwise be unnecessary load on the body and risk to the patient. So that's the setting. And I won't go through the details, but we've been able to overcome both of those limitations associated with electronics that exist commercially today. The first set of challenges is overcome by deploying those types of materials in ultra thin open mesh type architectures integrated with soft elastomer based polymers. So you can create essentially electronics that have the properties of the epidermis. And so these are advanced wearable devices that allow you to really place the electronics at any anatomical location that's relevant to a clinical need or a monitoring function. So moving from the wrist and the finger to relevant parts of the body. In devices that can laminate and establish persistent physical interfaces to the skin for wireless continuous sort of ICU grade monitoring, but outside of an ICU is the vision. And we've been working on this for about a decade and have a pretty good handle, on how to do that, and have correlated in many cases, the data streams coming off these devices to clinical gold standards. So I won't say a lot about that. The first sort of clinical need we focused on, addressing with that technology is, in fact, continuous vital signs monitoring in the neonatal intensive care unit, where the kinds of wired-based systems with external boxes of data acquisition electronics and adhesive tapes is really ill-suited for that class of patient. And so we decided, if we could make this wireless skin-like technology work, we get rid of that rat's nest of wires, get rid of the invasive tapes, get rid of the expensive external electronics boxes, and replace all of that with 1, 2, or 3 of these wireless skin-like devices. And we've been able to do that over time. We published the first integrated system in spring of 2019. These are battery-free skin-like devices. A pair of them allow us to reproduce everything that's done in terms of vital signs monitoring in the NICU today. One device goes on the chest, the other goes on a limb, and we capture everything that's currently recorded, even in level 4 NICUs that we have here in the U.S. So heart rate variability, respiration rate, core body temperature, and blood oxygenation. So you can do all of that. And as I mentioned, clinical grade in terms of the data quality, and sometimes better than clinical grade, because eliminate a lot of the failures and a lot of the motion artifacts that come through the wired interfaces and the taped based based fixation schemes for integrating the biosensors with the skin. So I won't go through the details, but this is sort of a summary of data that we've collected in an active functional NICU here at Lurie Children's Hospital, Prentice Women's Hospital as well. So we've done the NICU, we've expanded into PICU as well. So we have partnerships with Draeger, we work with GE, Space Labs, Anthem. We have a startup company that's attempting to scale those technologies, move them into manufacturable low-cost forms, and get them installed, ultimately hospitals worldwide, focused not only on the developed world, but also lower and middle income countries through funding from the Bill and Melinda Gates Foundation and the Save the Children organization, where we're deployed now in Kenya, Ghana, Zambia, India, Pakistan, and Mexico. So really addressing emergent needs in resource-constrained areas of the globe as well. Thinking about cost is an important additional metric. So that's kind of one of the platforms that go into this closed-loop autonomous electrotherapy system. The other one that I mentioned before is the implantable component, the component that actually interfaces with the heart. And the ideas that I just described to you for skin-compatible electronics apply pretty well to implantable devices in general. And we've been very, very active in that space, interfaces to the brain, the heart, kidney, bladder, spinal cord, peripheral nerves, a whole host of target locations within the body where we can do electrophysiological measurements, we can deliver electrical stimulation, various kinds of sensor modalities can be deployed in that way, in these soft sort of tissue compatible forms, using those same engineering principles that I mentioned before. So our initial focus with these kinds of technologies are sort of two regimes of operation. One where you might envision these platforms as advanced surgical tools or advanced surgical diagnostics used in an operating room, for example, where the residence time on the targeted tissues might be measured in hours. That would be an interesting set of opportunities. We're very active in that area. And then on the other end of the spectrum, in terms of residence times, you could imagine devices as permanent implants, where the relevant time scales might be measured in years or decades, or life of the patient ultimately. And I think that's another regime that we're very interested in. But what we were alerted to a few years back is that there might be opportunities for these sorts of soft implantable technologies for an intermediate sort of time scale of use, where you might want the device to operate for a time period aligned to a biological process such as wound healing or surgical recovery, for example, where the device could provide therapy or monitoring function, and then you ultimately wouldn't need the device long term, and so you'd like it to just disappear without the need for a secondary surgical extraction procedure. And so we got interested in that, and we're able to address the key challenge, which is, existing forms of electronics are permanent. How do you make them water soluble? How do you build them out of materials that can dissolve into biocompatible end products? It turns out you can do that. And I won't go through all the details of their entire sets of electronic materials and manufacturing approaches that we've now put together that allow you to build these kind of transient or bioabsorbable electronics. And that's the other key component in this overall electrotherapy system. And so if you have those two platforms, skin interface monitoring and power delivery electronics, again, that interface on the skin, and you have these transient implants, what might you want to do with those two platforms used, in coordinated operation? And you think about all sorts of monitoring functions, and we've sort of explored that, but I'll focus on electrical stimulation. And if you could do that, then what sorts of stimulation would you like to apply, and how could that be used clinically? And so then you look across the landscape of existing implantable stimulators, and there are a whole set of different sorts of opportunities, very, very exciting. But the one that we decided to pursue was based on inbound interest and requests for technology that we were receiving from the interventional cardiology group here at Northwestern, and that is in temporary pacemaking. So frequently, following a cardiac surgical operation, surgeons will place a temporary pacemaker to pace the heart as necessary during the recovery period following that surgery. So if the heart rate drops below a threshold value, they can come in and use the pacemaker to pace the heart up to a safe, sort of healthy heart rate. But ultimately, if the patient recovers from the surgery, as is mostly the case, you don't need that temporary pacemaker long term. And so it needs to be extracted. And that extraction procedure has risks associated with it because of the fibrotic capsule that sometimes develops between the pacing leads and the cardiac tissue during that period of operation, so that removal can tear the scar tissue, but also damage the healthy cardiac tissue as well. And so that's where the transient stimulator becomes important. And so this is an example of that device. It's wireless, it's battery free. It provides electrical stimulation of the surface of the heart. It couples to a corresponding skin mounted device that goes on the chest that allows measurements of ECG and delivery of electrical power to this device using magnetic inductive coupling. So it can control the pacing, that's being delivered to the heart wirelessly through an interface to this transient implant. And so we demonstrated that device on small animal models, mice and rats, medium-sized animals, rabbits and dogs primarily, and also on human hearts from organ donors. And so this technology can capture cardiac rhythms across a very wide range of cardiac sizes and works quite well. So this is what the entire system looks like. I have 1 or 2 minutes here and then I'll wrap up. You have a collection of skin mounted devices. The minimal collection is just one device that goes on the chest. It's measuring ECG continuously, so tracking heart rate. And it also has this wireless coupling capability to deliver power and to control that bioresorbable cardiac stimulator, which is sitting on the epicardial surface to deliver the stimulation. And the whole thing can operate in that closed loop manner without any physical tethering to external electronics for monitoring or for power delivery. And so it's transient. The entire system is transient in the sense that the implantable component is bioresorbable. The other components can just be removed from the surface of the skin after they're no longer needed. So this is the kind of use case and the benefit to the patient, which is ultimately earlier release from the hospital. That's kind of the vision. Decouple them from hospital apparatus, allow them to return to home where they can recover more quickly and more effectively by use of these advanced body integrated devices. So that's the clinical scenario. Here's some of the animal model data. I won't go through this, but it does operate in a fully autonomous, continuous fashion. Now the chest unit represents the minimal device portfolio for the skin, but you can add additional components and provide a more sophisticated machine learning based method for doing the closed loop control. And so I'll just conclude by noting that this is an example of these technologies in the context of temporary pacemaking, but any kind of temporary electrotherapy could be delivered in this way. And as I mentioned at the outset, we're doing quite a bit in nerve stimulators for accelerated healing and rates of nerve regeneration, bone stimulators as well. Other kinds of devices can be operated in this manner. So that's all I had to say. I'd be happy to open it up to questions. It's a combination of these two technology platforms in service of this specific clinical need. So I'll just mention that very highly collaborative group, deeply engaged with the clinical medical community, but also collaborating with others in engineering science as well. Set of senior PIs that we work with, but we also operate a very large group involving graduate students and postdocs, very talented people. They do all the work. I just get to talk about it. So I always like to conclude my talks by acknowledging them for their hard work and great ideas. So thank you very much again for having me today.
Well, thank you very much, John. This is really impressive, very fascinating, and congratulations again for really the wonderful work that you have done. I'm sure that what you are presenting here is a platform. So essentially, it is, as you said, the application are really, I would say, it is quite unlimited in somehow. One other question I may have for you is essentially, you show that the resorbability, it is one of the key components. Now, can you make different polymers or different technology which may allow for longer time to stay in? So can you do, say, few days to few weeks to few months or few years?
Yeah, it's a great question. As you might imagine, the engineering challenge is you're attempting to build a device that ultimately disappears completely without a trace, and at the same time, you want it to operate in a perfect, stable manner over a relevant time period. So those are two, radically conflicting sets of, requirements. So it gets down into the details of the actual materials that you're using, the polymer chemistry, the various kinds of conductors and semiconductors that are needed for the electronics, and not only the materials but the nature with which you're putting those materials together. So sort of the design architectures associated with these devices. So I would say the current state of the art for us is that we can do a pretty good job for stable operation over maybe a few weeks, 2-3 weeks, something like that, where the devices ultimately dissolve and completely disappear over a subsequent, time frame of months, maybe a few months. So a few weeks operating, a few months completely gone. We would like to get to regimes that you're suggesting, where you might want the device to operate for a year, or maybe 2-3 years, and then dissolve and disappear. That's pretty challenging. I mean, it's a great topic, and it's one that we're exploring, in our research. We don't have that capability today. We would like to move in that direction. I think in particular, bone stimulators are kind of pushing the envelope of what we can do. You might need 2-3 months in that case, and that's a little bit outside of the envelope of what is possible today. The trick is, how do you encapsulate a device with biofluid barriers that keep water away from the electronics, which would lead to corrosion and electrical leakage to surrounding tissues. How do you make those barriers very robust, but in materials that are bioresorbable and water soluble? That's the essential challenge, encapsulated in kind of compact form in that way. So I think it's a frontier opportunity, and it's one that we appreciate and are working on, but it's pretty tough also. So, I think it'll be possible, but we can't do it right now.
Very good. So the other question is, of course, I am a clinical electrophysiologist, and I'm dealing every day with cardiac pacemakers, different sort of cardiac pacemaker. Now, of course, what you showed is for cardiac surgery. So the question is, can we, as clinical cardiologists, electrophysiologists, can we do these like foldable and to put in a catheter that you can really deliver where in the spot that you like to be?
Yeah, another great question. So this is in fact one of the devices that I was just showing. So that's kind of the size and kind of the shape and the form factor. I'm sorry, I tried to stabilize this thing. So it's pretty thin. It's maybe the thickness of a few sheets of paper. It's a polymer material encapsulating the conductive traces and so on. So it is flexible. I'm not sure if you can hit the radius of curvature that you would need to really roll it up tightly so you could kind of insert it with a catheter. That's the platform we've published on, and the largest component part of that device is actually the antenna that's capturing power wirelessly, from the skin-mounted patch. And what we've developed and have not published yet is an alternative to that power source that involves electrochemistry. So it's essentially like a dissolvable battery in a sense. And because we've been able to develop that, the size of the device that we have now is much, much smaller. It's only about 1 by 2 millimeters. The whole pacemaker is about the size of a grain of rice. So we can just inject it directly with a hypodermic needle. So we'll be publishing that soon. We've stripped out that big antenna, and that's something that we're quite excited about. We think we can just inject it directly, superficially into the cardiac muscle, maybe down a millimeter, into the depth. So we don't need to worry about an adhesive interface to the surface of the heart. Just inject it right in, and I think that's where things are going.
Wow, this is really quite impressive. So I like it. So the other question is, I may have is about interference. I may imagine that this device may have different sources which may either disturb or distorts the field of the transmission field. So you showed neonatology, as you said. So there are a number of external monitors, wires, and in general, in the intensive care unit, there are multiple sources of potential interference. So any issue with that?
Yeah, it's another great question. These are great topics, and we think a lot about them. So for the cardiac pacemaker, the wireless link between the skin-mounted device and the implant is based on a near-field phenomena. So it's near-field communications is kind of the mechanism. Yes. It's magnetic inductive coupling. So the range is very short. Probably, a few centimeters type of thing. So I think that reduces concerns around interference, from surrounding, sources of electromagnetic energy. So I don't think that component of the wireless system is very susceptible to interference. And because we're delivering fairly large amounts of power, well, enough to power the pacemaker, not in an absolute sense, but relative to ambient sources of radio frequency power, it's large, and so we can kind of ignore interferences at that level. The other aspect, and I think this is probably more what your question refers to, is what about the wireless data transmission link, from the monitoring device to the external recording system. And we're using Bluetooth. We decided to use the standard for wireless communications in electronics, consumer electronics, because of cost considerations primarily. We're trying to, hit cost targets that Gates Foundation is interested in, lower and middle income countries and so on. And you pretty much have to go with Bluetooth because then you can use, an install base of smartphones as monitors essentially. So Bluetooth is fairly well developed in terms of, how it, allows rejection of ambient electromagnetic interference. So I would say that we haven't seen any practical difficulties. It's something that we remain alert about and aware of those possibilities, but we haven't seen it. I would say, in a NICU or an ICU in general, an operating room, there are lots of metal obstructions. It's non-trivial. You kind of have to think about reflections and obstructions and so on. And we really sort of optimize the antenna designs, and we optimize the transmission power that we're using to overcome those kinds of passive forms of interference. And we've been able to manage those challenges. They're important ones, but they're not prohibitive. That's been our experience.
Excellent. So last question is about, I think everyone is aware that some of the patients may need an MRI. And of course, now there is the question of MRI compatibility and potential stimulation by a very powerful antenna like you see in the MRI. Yeah, we've studied that in great detail. Another very important factor in how we make engineering design choices. So the antenna that we use to receive the power, it has a certain resonance frequency. So it's not really receiving power at frequencies outside of that resonant window. And so if you are careful about the electronics design, you can ensure that resonant frequency is non-overlapping with the frequency used in your MRI system. And so if you do that, then they're essentially decoupled, the wireless operation of the devices and the wireless operation of the MRI. You have to pay attention to it. But we publish the details, simulation, experimental details. We look at you quantified, parasitic heating to the extent that it occurs, during MRI imaging. And all of those results are published in that paper from 2019. So very important issue, but it's manageable. Well, this was really a great story and a really great presentation. Thank you very much, John. It was really quite informative. very fascinating, and I hope to have you again with us when you will do your injectable pacer. So that will be really, really nice things to have. With that, I really like to close, and again, to thank you very much for your availability. Again, congratulations again for the excellent and outstanding manuscript in Science. And here I say you bye-bye for now, and see you soon.
Okay, great. Thanks again for having me.
Bye-bye.
Bye.